Like Kelsey said, my name's Derek Parker. I'm a software engineer at HashRocket. Today I'm going to be talking about a project that I've been working on called Delve. So right off the bat, I'd like to say a huge thanks to the organizers, not only for bringing this all together, which is phenomenal, but for giving me the opportunity to talk about my project in front of everybody. I really appreciate this opportunity. So the project I've been working on, like I said, is called Delve. So just so I can get a temperature, how many people have heard of Delve before today? Oh, that is awesome. Very cool. So for those of you who haven't heard of Delve, I'll explain a little bit about it. Delve is a debugger for the Go programming language. It works by parsing various information out of a Go binary, collectively known as the dwarf debugging information. It coordinates with the operating system and the CPU to facilitate manipulating your program so that you can explore it and try to figure out what's going wrong. It does not do any kind of source rewriting. It's more in line with a tool like GDB. Speaking of GDB, why a new debugger? Why reinvent the wheel, especially such a large wheel, right? This project, I've been working on it for quite some time, and it's a relatively big undertaking. So why go through that hassle? Why do that? Aside from the fact that it's an incredibly fun project to work on, I'm having a blast working on it. There's also some technical reasons and mumbo jumbo that I'll get into later. But like Peter, I'd like to begin with a little story. Story time. So it all began a couple years back on a cold, wintry evening in Chicago, which is slightly redundant. It's pretty much always cold in Chicago. And I was giving a talk at a local Go meetup, aptly named Chicago Lang. And I'd given several talks there before, so I was feeling pretty comfortable. And this time I happened to be giving a talk about GDB. Now, as I said, it was a couple years ago, so I was young and naive. I didn't know what I was doing. I knew GDB had some faults, but a lot of the folks who go to this meetup come from like a Ruby background where they're really into pry, and they have this powerful tool called pry that they can use to debug and inspect their program. A lot of them haven't even heard of GDB, so I figured I'd go ahead and introduce it. So things are going well. I'm going through the slides, presenting all of this knowledge to these folks, and it's going really great. Then it comes time for a live demo. So this is an artist rendering of me giving a live demo. So it's going good. So I'm open. I switched to my terminal. I got my shell going. I'm about to do some like hardcore computing in front of all these folks. I'm about to fire up GDB, start inspecting a program, maybe dump some registers just for the wow factor for some of these people. And it's going pretty good. It starts off really well. I'm able to do some basic things. But once I start to get a little bit braver and try to get a little bit creative, GDB decides to crash. And it crashes pretty hard. So there it was, looking like a fool in front of literally tens of people, right? So it's just a nightmare. Just absolutely not the position that you want to be in. And as I was up there, red-faced and embarrassed, the only thing I could think of was, GDB must be destroyed. Wrong way. Again, GDB must be destroyed. It's worth saying twice. But with fire. So what we really need is an alternative tool. The existing tools out there don't work. They were created a very, very long time ago where the programming language of choice would be C or C++, which still kind of is today, but we've grown a lot as far as languages and the things that we want to do, and the types of languages that we want to debug. And existing tools, they're not one size fit all. There's problems. We really need something that's Go-centric, something that really understands Go and is built specifically for Go. Go has a lot of interesting nuances, which a lot of those are some of the same features that have brought us all to be Go developers, but as I'll explain later, they make it really tough for existing tools to debug. And lastly, and I think this is one of the most important things, at least to me, we need a tool that should be easy to use. So the entire Go tool chain is extremely simple to use. Go build. You've built a binary with optimizations already. Everything's good to go. Go test. You can start running your tests. You don't have to do anything special to get up and running with the Go tool chain. And in my opinion, the debugging story shouldn't be any different. Because let's face it, if you're using a debugger, odds are things already are not going your way, right? Like your program's not working, something's going wrong, you're already frustrated. So why introduce more steps into finding the solution? Why introduce more frustration? So what happened? Why did GDB crash? Put simply, it got confused. Existing debuggers and existing tools, Go is different enough that it can confuse these pieces of software. And I'll explain that a little bit more. So why? What parts about Go confuse existing debuggers and existing tools? I'll touch on a couple things. First off is Go's execution model. It's very different from existing programming languages, something like C or C++. We'll also talk a little bit about how Go does stack management and how that can affect certain debuggers. And lastly, we'll talk about, as I mentioned earlier, Go build will just do everything for you, but sometimes that's not what you want, especially if you're trying to figure out what's going wrong. So let's begin talking a little bit about the execution model. One of the first things that I'd like to bring up is the defer statement. Now, a lot of times, defer statement is going to be used for something relatively inconsequential, right? Cleaning up file descriptors, closing up like connection to a socket or something like that. But sometimes you do something in a defer statement that might change the return value of your function. And the code that gets executed in that defer statement can have an impact and can introduce bugs in your code. If you're using an existing tool, something like GDB or LLDB or something, those tools don't know about defer statements. They're not going to follow the flow of execution to the defer statement. So I'm sure everybody is familiar with defers, but just a quick overview. A defer is a function that is guaranteed to run after your function returns. So when an existing tool starts to think it's getting to the end of a function, it's going to figure out the return address, set a breakpoint there, and continue happily there. That doesn't work always, especially with Go, because there's other things that happen in the meantime. And if you're using an existing tool, this type thing is never going to be exposed. You'll never enter in the defer statement, and you could overlook a bug completely. Secondly, I'd like to talk a little bit about threads versus Go routines. Now, not that they're on the same plane as each other, but if we think about existing tools, if we think about something like GDB, it's planning to deal with a relatively standard process. So your standard process is going to be, depending on operating system nuances, a process composed of potentially many threads. And in the case of an existing tool, that's going to be the smallest unit of execution, is a thread. In Go, that's simply not true. Go has threads, obviously. It's a regular process with threads. But it also has an added layer of these Go routines, which are cooperatively scheduled on top of the threads that are being scheduled by the kernel. So let's talk a little bit about the Go scheduler real quick for some of the folks that may not be explicitly familiar, may be familiar that it exists, but take a little bit of time to introduce some of the cast of characters that make up the Go scheduler. So the first element that we have is the P, known in the scheduler. So that's the processor. So when you're setting Go max procs, the environment variable, or doing it in runtime, this is actually what you're modifying. A processor is needed to actually execute Go code. On top of that, we have what's known as an M, which represents an actual operating system thread. An M needs to have obtained a P to be executing Go code. So you can have more threads than you have Go max procs. Go max procs, as I said, actually only affects how many threads can actually be running Go code at any given time. And then we have what we're all familiar with, right? One of the things that probably brought a lot of us to Go in the first place is the Go routine. So the processor is the execution context. It also holds the runnable Go routine queue. How does all of that affect debuggers? It kind of goes back to Go having a non-traditional execution model. So it brings into light things like context switches. So what do I mean by context switch? There are various points in your program where they're called scheduling points, where a Go routine could be paused, put back on the run queue, and potentially picked up by another thread. During normal execution of your program, that's not a problem. Go's scheduler is really great at multiplexing these Go routines onto different threads, and it aids in a lot of the great parallelism and concurrency. But for a debugger, it can be kind of painful. If the code that you're trying to debug all of a sudden switches over to another thread, that can be very confusing if you're not expecting it. It can also cause GDB to hang when a context switch that it's not expecting happens and the code switches. GDB not knowing about the scheduler at all could cause the program to just hang when one of these context switches is about to occur. So what points in your program could one of these context switches happen? So you can apply one manually by calling runtime GoSched. It can happen during a blocking syscall, a wait or a sleep or something like that. Channel operations could trigger a Go routine to be paused and put back on the run queue. Garbage collection could potentially cause it as well. And a Go statement, I believe. It's possible for, I believe it's the Go routine that invokes the Go statement to be paused and put back on the run queue so that the other one can start immediately. So let's move on to the next point, stack management. So any pure Go function is going to do a little bit of runtime stack inspection. And this is very, very important for a couple reasons, but it can have effects that can prevent certain things from being able to happen in a traditional debugger. So any pure Go function is going to have a function prolog stack check. And that's important because one of the great things about Go and Go routines is they're very, very cheap. So they're initialized with a small stack. So when you jump into a function, checks to see if it needs to grow the stack. And if it does, it'll allocate a new stack, copy everything over, and switch to it. But this can confuse debuggers. If you want to do something like call a function in your program from within GDB, What GDB will try to do is set up a dummy stack frame and jump into that function. When GDB tries to do this, it'll actually crash the Go program that you're trying to debug, because as soon as it jumps into that function, it's going to start looking up the stack and find something it doesn't like, and it's just going to panic and blow up. So that can be very frustrating, especially for a lot of folks who come from dynamic languages and are able to just willy-nilly invoke functions, call methods, and do anything that they want to inspect their program. Lastly, touch a little bit about on compiler optimizations. So by default, the Go compiler is going to provide a couple optimizations. It's going to do function inlining, and it's going to registerize variables. Function inlining is particularly a problem with debugging, because what the debugger is going to try to do is take a look at where you are, where the program counter says you are, and relate that via the symbol table to where it came from in the source code, so that you can actually see where you are in your program. With function inlining, this can be a problem. Also, registerizing of variables, depending on how the dwarf information is written out. If it's written out expecting everything to be on the stack, you can attempt to read a variable and just get garbage back, because the value of the variable is actually in a register. It's not being stored on the stack. So these optimizations, these default optimizations, are great for production, but they're not great for trying to debug a program. So the solution is to pass some flags to the Go compiler. But again, the whole Go tool chain is very simple and easy to use. Why go through an extra step? So let's introduce Delve a little bit. This is all you have to do to get up and running to start debugging your program with Delve. Extremely simple. That single command is going to compile your code with optimizations disabled for you. It's going to start your program. It's going to attach to the process, and it's going to land you at a prompt ready to start debugging your program. If you have a standalone package that doesn't have a main, you can use Delve test. Hopefully you're writing tests for your library that you're hoping people will use. So this will do something similar. Compile a test binary, start the program, attach to the process, and land you at a prompt ready to start eradicating bugs. Additionally, you can debug existing binaries, and you can attach to a running process. These come with the same caveats as I introduced earlier, where you could be dealing with an optimized binary, and you can run into some of the same exact issues, even though you're using Delve. So to continue the introduction, let's take a little trip down memory lane and go over the history of Delve. So last year's GopherCon, there was a talk that got canceled or something, and what ended up happening is a Q&A panel of some of the Go core developers, which was really great. One of the questions that was brought up was, what's the Go debugging story? And I believe it was Rob Pike mentioned something about it's something that they admit is a problem. It's something that definitely needs to be addressed. But obviously, those folks are very, very busy writing this programming language that we're all assembled around. So it doesn't leave a lot of time for some other projects. So that planted a bug in my ear a little bit. And about a month later, I put the first commit in on Delve. A couple months later, I announced it. So it was a solo effort for about the first 4 or 5 months. And when I announced it, it was still very, very alpha. Only supported Linux. And it was mostly to help drive contributions. It was kind of kept under wraps a little bit. It was just a fun project to work on. Then by the time it started becoming something useful, I figured might as well get some other folks in on it. And that brings us to today. The project has grown a lot. And thankfully, I have the opportunity to take the time to speak about it and hopefully get some more people interested in it. So the state of the project as it is right now is pre-1.0. So what does that mean? The project is still very much in active development. You could use it, and it could do something weird and frustrate you. So I've been hesitant to slap a 1.0 label on it. So far, we have 22 contributors to the project. And I'd like to take this time to say thank you to anybody who's contributed to this project. Open source is amazing, and I appreciate anybody who takes the time to help me on a project that I'm very excited and passionate about. The code base is a mixture of Go and C. I would like to write it in as much Go as I possibly can, but to interface with some of the lower level syscalls on OS X, some of the mock stuff, I was unfortunately forced down into C. It supports Linux in OS X. It has initial support for editor integration through JSON RPC, so you can run it as just like a debug server, and it can be communicated to via your favorite editor, Vim, or whatever IDE you happen to enjoy using. And a lot more commands have been implemented. When I first announced it, it's very rudimentary, break and continue and some other just basic commands. So I kind of want to go through quickly of how can you use this. Let's talk about some of the commands that you can use. Particularly, let's talk about some of the control flow commands. So you can set a breakpoint, right? You can set a trace point. The difference there being if Delve hits a breakpoint, it's going to stop the world, stop your program, land you back at a prompt so that you can inspect. A trace point's just going to say, hey, I got here. And optionally, you can provide flags to say, give me a stack trace of n depth whenever you get here, and also give me the value of these variables whenever you hit this trace point. So prevents you from having to do things like print line debugging. You have all the power there. So you can continue your program. You can single step it. So that's actually going to be one CPU instruction. It actually does a real hardware single step, one instruction at a time. We'll step into functions. Next, we'll step over to the next source line. Stepping over functions, you can switch to another thread if you're curious about what's happening there. And you can kill the current process and restart it so that you can start debugging your program again without having to leave Delve. It also provides some informational commands. So you can use the thread command to print out the status of all threads of the process. GoRoutines will print out the status of all of the GoRoutines that are executing in the process. Breakpoints lists all the breakpoints that you set. You can evaluate a variable. And there's also some of the GDB folks might be familiar with the syntax in info command with subcommands. So it takes an optional regex. So let's go over some of the commands. Args print the name and value of all arguments to the current function. Funcs, all of the defined functions that are in the binary. Locals, all package locals, or all locals in scope. Sources, all of the actual source code that went into compiling this binary. Vars, all package variables in the application. And regs, so you can print out the value of the CPU registers. Additionally, the Go standard library has this function runtime breakpoint. And Go will handle it by realizing that it's within this function, step out of it, and put you on the next line where you want to be. So it's a simple way of, instead of invoking the debugger and having to set a breakpoint manually, you can set this function in your source code wherever you want to stop, fire up the debugger, hit continue, and it'll put you where you want to be. So let's talk a little bit about where Delve is going. So obviously, we'd like to get to a 1.0 release. I want this to be a tool that everybody can use just as part of their daily developer toolkit, something that they can reach for, a reliable debugger to help solve their problems. Support for Windows. I believe in the Go model of, hopefully somebody will contribute this, because I'm not going to install Windows on any of my machines. It's an open source project, and I'm not paying for a Windows license. Full support for editor integration. So I'd like to see more integration with Vim or whatever your favorite IDE is, or Emacs. And more advanced commands. So I'd like to improve print and allow setting of variables. I'd like you to be able to call a function and things like that. So I have a little bit of time, so let me get into a little bit of how to use it. Now, thankfully, I think I'm lucky because Kelsey's here. He does live demos all the time, so hopefully some of that good live demo vibe will rub off on me. So like I said, we can run delve test and compile a test binary and jump into it. Continue it, and like I said, if you have the runtime breakpoint function, it's going to recognize it. It's going to put you on the next line exactly where you want to be to start inspecting your program. So let's run the main process real quick. So let's set a breakpoint at main, continue, and kind of see what's going on a little bit. So we have this function, convert to the number 10. If it equals 10, it works. If not, there's a bug. So let's do, there's a bug, right? Oh, it's terrible. So let's jump back in and let's explore a little bit. So I just kind of want to go over a little bit of some of the commands. So let's set a breakpoint at convert to the number 10. There's readline support, which is pretty nice. So here we are. We can inspect things like, take a look at what threads are running. It'll give you the source file, the line number, the function that it's on, and also the address. You can also take a look at GOROUTINES. So that'll print out the GOROUTINE ID, where it's at, and how many GOROUTINES are currently running in the function. We can start nexting through the program, so we can kind of see what it's doing. And like I said, it's going to properly follow through to defer statements and keep going through flow of execution there. And then we can just keep going, right? We can print out the value of a variable, and it'll return it to us. Obviously, it's not 10, so there's a bug. Yeah, so that's just kind of like a brief introduction. I think I'm running a little bit low on time of some of the commands that you can do. If you want to see a little bit more of a demo, or if you want to use it a little bit more, check it out. Feel free to find me around, and I'll be happy to show it off or help somebody hack on it or something. So I'm about out of time. I just want to say thank you. Again, my name is Derek Parker. You can follow me on Twitter at Dirk the Daring for some updates on Delve and probably a lot of pictures of my dogs. And that's it. Thank you.